So let's do this quick one. Okay, this is about buoyancy. Basically, the topic regarding this problem is buoyancy. And it's, well, it has its issues, but I don't think it could be very complicated. Okay, so this steel block lying between water and mercury, it's floating there. Okay, so we have its specific gravity. And this thing, as I said, it's floating at this interface of mercury and water. What is the ratio of the distances A and B for this condition? That is, how much of this steel block is in water and how much this steel block is floating. I was going to say lying, but it's there in mercury. Okay, so let me start with the basics of this one. Maybe it's not too complicated, but let's just see. We have two different parts. This guy is A and this guy is B. Nothing new so far. So what you will see is that the water is pushing up its buoyancy force due to the water, okay? And you also have the buoyancy force, I'm gonna put it over there, due to the mercury. Okay, so Hg, you know, it's mercury. W, it's water, but it looks awful, so I'm gonna change it a little bit. So with this one, hopefully it's better, W. Fine, and also there is missing the weight. So the weight is happening at the center. I'm just gonna try to put something like this, and this will be the weight, okay? So we can put an equilibrium equation, remember? So sum of forces in the y direction should be equals to 0 because this steel block is not moving. So if it's not moving, we can put two guys going up, which is the buoyancy force due to the water plus the buoyancy force due to the mercury and minus the weight of the steel block. Okay, so equals to 0. Now we already have our equation. We still do not see explicitly A or B, and we want to find something about it, but we can actually get it. Let's just see about the buoyancy force due to the water. So if you remember, this has to do with the density of the water times the gravitational acceleration, the G, times the volume of the body submerged in water. So only the thing that is in the water, it's producing the buoyancy of the water. And I can also put the same thing for mercury. So I'm gonna put Hg for the density, the G and the volume that is lying regarding the mercury. Okay, so, and also the weight of the steel. The weight of the steel is rho of the steel times the G times the volume of the whole steel block. Okay, so there you go. I have just rearranged a little bit this equation, but now I can put more information. Maybe you agree with this. I'm gonna think that this has a dimension of L, okay, here, and at that place, it has a W. So it's the same one here and there. So I'm gonna think that's the shape of that one. So L and W are not known, but maybe I don't care about how much those things are. That's why they put you just a 2D image. So because it seems that it's not very relevant. So what you will put over here is the density of the water times the G times the volume. And maybe you agree with me that the volume should be for just the part that it's lying at the water is this. Okay, this one actually. Whoop, just the upper part of this body. Okay, just this one. And that one is gonna be, well, I'm gonna use this one. This one is the volume would be A times L times W. Okay, that's the volume lying in the water. Now I'm gonna put the same thing for the mercury, but with some other information. This is the mercury, the G, and the volume lying in the mercury, which is, I'm gonna put something else, which is, this one is P, L, and W. Okay, we are almost there. Now this, I'm gonna just put rho S of the steel, G, and the volume of the whole body. The volume of the whole body should be, I'm gonna put it here with blue, A plus B, okay, times L, W. And with that, now I can jump into my equilibrium equation and have everything that I need. So I will put here um, rho W O G A L W, good, plus rho H G G B L W equals, I'm gonna put it this weight, I'm gonna put it from the right part, and this thing will look rho of the steel, density of the steel, G A plus B LW. So maybe you see that LW is not relevant in this case. The G is also appears in every other term of this equation, so I don't actually need it. And with this, I will try to put this, I will divide everything by the density of water. So I can get just the specific gravity of all these substances. In this case, this one is just one. So I will leave myself with this equation, which is A plus a specific gravity of mercury, okay, B equals to a specific gravity of the steel, A plus B. Now, what I want to do is I'm going to divide everything by B. So this guy is B, this guy just goes out, and this fella is like this. I'm going to do it like that. Therefore, I will get myself A divided by B plus SGHG equals to, maybe you see it, AB times the specific gravity of the steel plus the specific gravity of the steel, because B divided by B is just 1. Okay, so you see that this is a common factor here. I will put this fella over there, and with that, oh yeah, let me just move down, and I will see that I will pass this fella over there. So I will get Sg of the steel, sorry, minus plus Sg of the mercury should be equal to A divided by B, and this is the Sg of the steel minus 1. Okay, so now we're about to finish. I just need to do some algebra here, which is A, B equals to Sg of the mercury, okay, minus Sg of the steel, and everything's gonna be divided by Sg of the steel minus 1. So it seems that the ratio of the parts where the steel block is inside that substance, whether it's water or mercury, just depends on the specific gravities of all the substance involved. So if I substitute everything here, I will get myself that AB equals to, let's just put these numbers, 13.56 minus of the steel, which was 7.85. Let me just check. Yeah, 85 divided everything by 6.85, because it's just 785 minus 1, you will get that. Therefore, what I have here for the AB ratio is just 0.833. And you can check that out. Maybe you will see that I'm right or wrong, but that is the answer of this problem. Okay, guys? So see you around later.